Okay, so we said then that the force that would be acting as gravity when we spin this habitat centrifugal means, literally, it means center fleeing. Centrifugal is center fleeing. So in other words, it's going from the center outwards. Okay, let's analyze this for a second. I want to demonstrate a way that you can easily show that this is a bogus force. It doesn't really work. So let's take regular gravity for a second. Regular gravity, if a person is standing on Earth, what are the forces acting on that person? So we got gravity pointing down, right? And we've got normal force pointing upward, right? Okay, are those an action-reaction pair?
Yes.
No, okay. Right, they're each pieces of an action-reaction pair, right? How come, somebody remind me, we'll go back to a good review here. Why are those, what's the easiest way to demonstrate that those are not an action-reaction pair? Okay, because they're acting on the same object. An action-reaction pair really is just illustrating the fact that forces always act between how many objects? Two. They have to, right? Forces are simply the interaction of two objects, right? So the blue vector, our weight, is really it's half of an action-reaction pair acting between the person and what? Earth, right? The center of the Earth. Does that make sense? So, right, so we've got the Earth down here. Earth pulls on the person pulls on the Earth, right? It's a mutual thing. Normal force, well, that's a surface force acting between the ground and the person, right? Okay? Now, if we, yeah.
Really quick, how quick is the Earth going at 1G? How quick is it rotating?
How quick is it rotating?
Yeah.
Like, you mean rotating or revolving around the sun? What are you talking about?
Rotating.
Rotating, oh, not even close. Yeah, not even close. If the Earth were spinning around so that the centrifugal force were 1G, that would be kind of a problem in what way?
Would we fly off here?
Well, you wouldn't necessarily fly off, but you couldn't. Yeah, it would be a problem. What would really happen with that? If you were on the Earth and you went to take a step, you're not going to be able to ever put much force on the Earth, right? You can't produce enough normal force to ever really do anything, right? You'd have to kind of jump up in the air, and then when you land, you can push off a little bit, but then you have a hard time stopping, right? Does that make sense?
No.
Well, because why are you able to? Could you be moving with the Earth, right? Hopefully. And so if you're moving with the Earth, you're moving around that circle at the center of the Earth really fast. And so the centrifugal force that's throwing you outward would be the same as the gravitational force throwing you inward, right? We're going to talk about this differently by the end of this period, because I hate to use the word, it's just eating at me to use the word centrifugal so many times, because it's a bogus word. But using that word, it's not going to work well, right? You're essentially going to be in orbit with the surface of the Earth around its center, right? We're not in orbit now. We're being supported by the Earth, right? We're moving around sort of fast, but not nearly fast enough to make much of a difference. And the demonstration of that would be if you stood on a scale at the equator, and then you stood on a scale at, near the North Pole. Are you going to see that big a difference? No, it's not very big at all. Tiny, tiny, tiny little bit, but we're not going nearly fast enough. Okay, good question. But you see that if we were, we'd be able to just tuck up into a ball and just kind of hover there above the surface of the Earth, right? Cool. It'd be a bad thing because eventually you're probably going to get slowed down by a little bit of the drag that would occur, and you'd start to kind of skip backwards along the Earth, and it would be a bad deal. Yeah. Yeah, you could. Yeah, exactly. Yeah. So anyway, so here we've got two pairs of action-reaction forces. Now let's look in the floor of our space station. So if this guy's standing inside the floor of the space station, same dude standing there. Okay, what are the forces acting on that guy?
Okay, so there's one pushing him out, right?
Well, is there?
No.
That's the thing. There isn't one, is there?
Isn't it just the same?
See, there used to be something down here pulling the guy.
Yeah.
It was the earth.
But
So like the energy that's spinning around is like, it's still affecting the person.
Well, it is, but there is one action-reaction pair acting on the person here. What is it?
the floor and the.
Yeah, the normal force, right? The floor is pushing up on the person, agreed? So there's only one force acting on the person, and it's that way,
Are we on a trampoline?
right? And as a consequence, the floor pushes on the person, so the person pushes back on the floor,
Yes.
right? But there's no other force going on. There's no like ring of matter out there that's gravitationally pulling this guy. He's in interstellar space where there's zero average gravity, right? So it doesn't work, right? What's going on though? Well, what's going on, I think we talked a little bit about this. Did we use the invisible car? We didn't talk about that, did we?
No.
Okay, so what if you were, let's look at this from a different perspective. If you're driving along in a car with a glass roof and somebody's hovering in a blimp or a helicopter over the top, and let's just say Clancy's in this car, she's in the passenger seat, and she's wearing a really bright hat. In fact, the hat's got a battery pack in it that glows. So we can see this really well from above. As she travels in a straight line at constant speed with the cruise control on, she doesn't really, no big deal, right? She's just moving along with the car. But when James, being kind of a wisecracker, turns really sharp to the left, what do we notice? Okay, we'll probably notice a couple things. We'll notice that if she wasn't sitting next to the door, if it's like a pickup truck with a bench seat that's been armor-all and was really slippery, what she'd probably do? Slides into the door, and then all of a sudden the door is locked, so they go flying out. It stops her from moving sideways in the car, and all of a sudden it starts to push on her, and what's it do to her motion as seen from above?
Stops.
It doesn't stop.
Well, it turns her.
She turns, right? But that's not natural. That's not what she wants to do. The law of inertia says that moving object, she's got some mass, she's got some momentum, she wants to travel in a straight line at constant speed, right? And so she doesn't want to turn, she has to be coerced to turn by the door, the seatbelt, or whatever. Something's pushing on her to push her out of that straight line path. But there has to be a force acting, right? Because she has now changed her velocity. She used to be going that way. A little bit later, if he stops turning, she's going that way, right? Change in velocity. Well, what is change in velocity over change in time? That's a quantity that we know. That's acceleration, right? So if her velocity has been changed during that time interval, she must have experienced some acceleration, right?
But James.
He didn't speed up. He had cruise control on the whole time. He just turned the car.
She.
So the speed didn't change, but the velocity did, because velocity is a vector quantity, right? Even though the magnitude of the arrow stayed the same, now it's pointing this way, right? So you agree there has to be, there was some acceleration there, because the velocity vector is different than it used to be. And so the only thing that causes acceleration is force, right? F equals ma.
So this is like inertia that's keeping the person on.
Exactly. So what's keeping the person on the ground is their natural tendency, not tendency, it's the law of inertia, right? Their inertia will always carry them straight forward at constant velocity unless they're acted on by some external force, which is the floor of the space station.
So then that's inertia?
So it's not really inertia, it's the change in inertia. It's the change in inertia. And technically, if we were going to do this as a calculus-based class, we haven't learned what momentum is yet, but I'll let the cat out of the bag here. Momentum is just mv. P stands for momentum, and it's just m times v is all it is, right? Well, technically, the definition of force is not ma. The definition of force, really, that's just what we tell you in an algebra-based class, but in a calculus-based class, we'll tell you that the definition of force is really dp dt. Okay, the mass is probably staying the same. Now, why do we call it dp dt instead of m times dv dt? Because m's a constant, right? No, it's not. If you travel at relativistic speeds, your mass changes. So it's not constant. If you travel travel at speeds that are some appreciable percentage of the speed of light, your mass increases. So you have to take that into account, right? So we haven't gotten there yet, but it's coming. So what's really going on here is what's making this person feel like they've got gravity, what's preventing their bones from degenerating, is that there's this constant normal force acting on them, right? Which is causing them to deviate from their straight line path into this continuous circular path, right? And so from our perspective, it's just as good as gravity. Same thing, right? It feels no different at all. As long as the space station, I can't remember what the number is. I should look it up. I used to remember this, but I want to say it's like 1.2 kilometers in circumference, something like that. That's the point at which you could spin this thing and have 1g centripetal acceleration and not notice the spinning. So you wouldn't always feel like you're dizzy. Yeah, so that's pretty big.
But what if there's like a window and we look outside, then would we know that we were spinning?
Oh yeah, you'd know, sure. Yeah, I mean, you could look outside and see that you're spinning. Just like on that ride we talked about the other day, right? I mean, you know you're spinning, but if you were daring enough to like stand up inside that big ride that goes around in a circle and they drop the floor, if you kind of stood sideways in that thing, I mean, it would sort of feel like gravity. It's not going to be a really good stand-in for gravity though, because the radius is small enough that you're going to feel a different acceleration in your head than you do in your feet, and so that's going to be a little weird. And you're going in such a tight circle that your ear has this ability to sense acceleration in your inner ear, and so you would notice that your orientation is changing fast enough that you probably end up yakking all over the place because your ear can't handle that, right? But if it's a big enough circle, your ear isn't sensitive enough to notice the fact that you're going in a circle. It just feels like a straight line, right?
So is that like when people get dizzy?
What's that?
That's when the thing
Yeah, that's why you get dizzy.
What
starts spinning around in a
if
circle.
you crouch down on her? Would it still be enough?
No, even then it wouldn't be enough. And you'd still notice that you're going in a circle.
Okay.
Yeah, there's no way around that.
Wait, so people that get sick on carnivore ride stick, that means their ears are better because.
Well, okay,
Like
it means,
their-
I guess better or worse, it means that they wouldn't be good candidates for astronaut training. Yeah, because astronauts are screened for the ability to not get sick when they undergo large changes in motion.
But they have like sharper senses too.
Well, probably they also have good eyesight. You know, I mean, there's a bunch of things you'd screen an astronaut candidate for, and or fighter pilot or anything. I mean, those people they'd have to have some tendencies that make them good at their job, so they're not going to get sick while they're flying the plane. They're going to not pass out when they take lots of, stuff like that. Okay, but let's go back then. So let's get back to our talk here then. So this is not a real force, right? This is an artifact of the normal force that's changing our motion. Let's explore this a little bit though, this centripetal acceleration bit. So anytime that we've got an object traveling in a circle, and we'll call it uniform circular motion. So it's going to be traveling at constant speed, but it's traveling in a circular path. We call that uniform circular motion. So let's have a little look at this.
But it's not constant velocity because.
It's not, you're right, exactly. It's not constant velocity, it's constant speed. Okay, so let's pull up. Just so happens, I've created a little something that might help us understand this better. So. There it is. Okay.
What'd you say?
Okay, so here we have a circle, just an ordinary circle. Let's add some stuff though. Let's add some position vectors. Okay, so we've got some object, and let's say that it's traveling around this circle, and at time 0 it's there, and sometime later it's there. So we're going to call this vector that's our position vector, and because this is a unique situation where it's uniform circular motion, we're going to call that position vector r, or r sub 0, or r naught in this case, right? Because it's always one radius away from the center, right? And then So our initial position is R naught, our final position is R, okay? Let's add some velocity vectors, okay? Now this is kind of cool. This is all set up in Geometry Sketchpad, so I can tweak this thing and everything changes accordingly, right? If I change the position of this guy, that's fine, it does that. I can change, if I change the length of this velocity vector, let's make the speed a little slower. They both get slower, right? Okay, but what James was saying is pointing out that it's not constant velocity, and we can see that, because this would correspond to our initial velocity, right? At any moment in time, if I'm spinning a rock around on a string and somebody cuts the string, in what direction does the rock fly?
Yep.
If I cut the string right here, does it fly off like that?
No.
No, it flies off tangentially, right? Think about that. We understand why that is now. Because an object wants to travel at constant velocity, right? That's what the law of inertia tells us. At this moment right here, the only reason it's not going to continue to travel at constant velocity is that there's some tension in the string that's providing a centripetal force. Now, I'll write that one down proudly because centripetal is a real thing.
What?
It's like 2 letters. Is that what we've been talking about?
What have we talked
No, we've been talking about centrifugal. Centrifugal, or centrifugal is what we say, is false. It's artificial. But centripetal force is the real deal. Centripetal force.
You could have fooled anyone with that.
Centripetal is just a couple letters different, but there's a big difference in meaning. Centripetal means not center fleeing. It means center seeking, and that's the true force that is pulling us towards the middle of the circle. In the space station, it's the normal force of the floor provides, and as evidence of that, if the floor were really flimsy and it broke, then what would happen to us? We'd go flying out into space, right? Does that make sense? I mean, we just fall through the floor, and then we just travel in a straight line out into the oblivion of space. On this, if a rock's on a string, and we cut the string and remove the centripetal force, then we're no longer going to be changing our velocity vector. We're just going to travel in a straight line with constant velocity, right? Okay, so if you wanted to swing a rock and hit something, I'm not going to release the rock I'm not going to release the string when the rock's there, or I'm going to hit somebody over there, right? I'm going to release the rock when it's right there, right? And then I let go and it continues forward, right?
Wait.
Not that I'm encouraging you to go out and sling rocks at people, but. Okay, so now let's look at this stuff here. So I want you to notice a couple things. I'm going to show you, so here, notice that these, of course, the position vectors, my initial position and my final position, if you can see that, it's pretty small. They're both the same, right? Measured in centimeters up here. I don't know, I don't know why. Ignore the units. The same thing would be true for where are my velocity measurements? Where did those go? Got it. Oh, there they are. They're hidden. Oh, fun.
Wow.
So there they are.
What is happening?
I broke it.
I do.
There's like a million of them.
Oh my gosh, what's going on? This
We good?
is craziness. Yeah. Here, I'll just do that. We don't need to have this in. I can just do it here. This is fine. I don't have to write on this stuff. So notice that what does this 6.50 represent?
That's the velocity.
Original vector.
Okay, so what would you label that? It's the length of the velocity vector. So what is that quantity? No.
So,
No.
It's a magnet.
The magnitude of a velocity vector we could call
speed at the time.
speed, right? Just speed, right? Because velocity is just speed in a given direction, right? It's got two components, the speed and the direction. So notice the speed stays the same, but clearly the velocity changes. Okay, let's do something else here. What if I take these vectors, and we know that we can, when we're going to do math with vectors, we can translate them freely, right? We can move them around as long as we don't change the position or the magnitude. We can move them around, and we do that all the time when we add up vectors tip to tail, right?
Right.
Okay, we add up components to represent some vector, right? Okay, so let's do that. let's take those vectors and let's just slide them over here and let's orient them tail to tail. So now here's I put a prime next to them so we can just see that they've been translated, but those are the very same vectors, right?
Okay.
And notice that the lengths haven't changed, right? The speeds are the same. Here's my initial speed, or initial velocity, there's my final velocity, okay? Let's go ahead and let's calculate some changes. Let's calculate the change in position vector, okay? So what's that gonna look like? Could you estimate, somebody kind of just describe visually what's the change in position vector gonna look like? And keep in mind that these are supposed to be vectors. So that's supposed to be a tail and that's supposed to be a tip. That's supposed to be a tail and that's supposed to be a tip.
Like,
But what do you
it'll
mean?
be like a portion of the edge of the circle.
It's gonna be close, it's gonna sort of mirror the edge of the circle. Yeah, if I put in the change in position vector, there it is right there, isn't it? Right? Think about this, because I know that initial position plus the change in position must equal the final position, right? Does that make sense?
Yeah.
Okay. Same thing for the change in velocity vector. If I want to show there's the starting there and ending there is my change in velocity.
Wait, but
Okay.
it's different than the blue one.
It is. You're right. It is a little bit different,
It's because it's not following the curve.
right? Okay, but you might notice something here. Look at the extremes here. They line up. If I were to go clear over here, they're opposite. Do you suppose that if I went right here, so that's 90 degrees, what do you know? What do you think is probably true about that angle compared to that angle?
They're the same.
Yeah, they are. In this case, they're both 32.1 degrees. Okay. Makes sense, doesn't it?
Sure.
Right?
Wait,
Has to be, because my initial position and my initial velocity are at right angles, right? My final position and final velocity are at right angles. So they're changing by the same amount, aren't they? Yep. Right? Okay, so here's my change in velocity. I'm gonna do one other thing here that's gonna be kind of interesting. Let's go ahead and let's look at the ratio of the change in position to position and the ratio of the change in velocity to velocity. Okay? Look what we find. The length of this vector divided by the length of that vector is 0.553.
Wait, which vector divided by?
So the change in velocity divided by, I could have used either one of these, but just call it, excuse me, change in position divided by position, right? So another way of thinking about that is the change in position divided by the radius of the circle that we're traveling in,
Oh.
right? Okay, we're talking about magnitudes. Look over here. If I do that same calculation over here, if I take the change in velocity divided by speed, I get the very same thing.
But what is that thing?
That's that angle right there. That's what I measured. I'm sorry. I measured the ratio of this side of the triangle to that side, but those sides are congruent, aren't they? Right? So I need to go back and write on this thing again. Okay, so we're gonna. Okay, I'll use purple. How about? Okay, so what that's telling us then is that the ratio of that to that is the same as the ratio of that to that. But this is an isosceles triangle by definition, isn't it?
Yeah.
Right? We know that those two sides are congruent, and we know that those two sides are congruent. And so if I know that those angles are congruent, what else could you tell me about the other angles?
They're also.
They have to be, right? Because I know that these base angles are congruent to each other, right? But by the triangle sum theorem, I know that the sum of all the measures of the interior angles is 180. So they have to be the same angles there, right? Well, I didn't even need all that stuff, but if I just take the fact that all the angles are congruent, what can you tell me about those two triangles? They're similar. Yeah, they're similar, aren't they? And so the ratio of sides should be equal, shouldn't they? Because the ratio of side lengths in similar triangles corresponding side lengths are equal, right?
So
Going
like
back to geometry, right?
half as big.
So, well, we don't know, I mean, we could vary, yeah, we could vary the size of the triangles, but it doesn't matter. The ratio of this ratio is gonna stay the same, no matter what, right? Because the triangles remain proportional, right? So that's, you might be thinking, okay, well, big deal. It's kind of cool to see that there's so much geometry involved in this physics, but there's something important about that. So we know then, we could do a little calculation here. We know that the ratio of dr, I'll call it delta. I just didn't have a delta symbol available to me in Geometry Sketchpad, but delta r over r must equal the ratio of delta v over v, right? Okay, let's do something else here. We know that the time that elapses between this point and this point is, by definition, we're going to call that delta t, right? And in calculus, all we're going to do in calculus, if we were to look at this same situation in calculus and want to do this exactly, using differentiation and integration, all we'd really have to do is just take a limit as delta t goes to 0, right? Okay, and we'll maybe talk a little bit about that, but not a ton today. We'll come back to that later. But this is true, right? Well, what if I just multiply each side by 1 over delta t? I can do that because this is an equation, so I can multiply both sides by the same thing, right?
But why would we want to?
Okay, why would you? You see if you can tell me, why would I want to do that? Well, the deltas don't cross out because the delta r is one thing, right? That's like one variable. That's the change in position, and that's the change in time. But do you see any quantities there that I could recognize and maybe rename?
Velocity.
Okay, look, we got velocity right there, don't we?
Wait, how is that velocity?
Because what's change in position over change in time? That's velocity, right? That's what we learned, average velocity, right?
But there's the r on the bottom.
You're right, so the r stays there. But
So
this
the
part
R
right
velocity.
here, that part becomes
Velocity over
v,
So v
right?
on
And this part right here becomes a, right? Everybody agree?
Yeah.
So when we do that, look what, now our equation ends up being v over r equals a over v. If I were to solve that for a, all I've got to do is multiply each side through by v, right? Look at the equation we get. This is hugely important. This equation we get is a equals v squared over r. Well, that is our definition of centripetal acceleration. That's the formula. How about that? Okay, good place to leave off. Good weekend. Beat Herm tonight.